See, so far we have seen only the basics of paging, okay? Actually, we have not seen how paging exactly works, okay? So what I'm going to do in this video is I'm going to take an example, a small example, and explain you very well that how paging exactly works, okay? Let's see this. They are given that process size is 16 bytes. Okay, size of a single process. We are considering a single process, and they are given that its size is 16 bytes. We also say that as logical address space of this of a process, right? Say logical address is address space of P1. Okay, and they have given that RAM size is 64 bytes. See, generally size of RAM will be very big, right? But just for understanding it better, I'm taking it a small number. Okay, 64 bytes. And we say that you know that we say the size of RAM size is physical address space, right? It is 64 bytes. Also, they have given that page size equal to frame size equal to 4 bytes. We always know that page size will be equal to frame size, okay? And they have given that as 4 bytes. Now let's find out, and also let us assume that they have also given that it is a byte addressable system. Okay? Byte, what do you mean by byte addressable system? Every byte of our RAM will be given a unique address. Okay, that is what we mean by a byte addressable system. Anyway, let's see this. What is the number of frames we will have? See, what is meant by number of frames? See, we have RAM, right? We know that we have RAM, fine. They have given that size of RAM is 64 bytes, which means the total size of this is 64 bytes. Also, they have given that size of a single frame is 4 bytes, which means single frame size is 4 bytes. Now, how many such frames will be present here? That is nothing but 64 divided by 4, right? See, this is RAM size. So, what I want to tell you is number of frames is equal to physical address space divided by frame size. Okay, physical address space is nothing but 64 bytes. I can write 64 as 2 power 6. Okay, it will be easy to actually simplify. Physical address space is 2 power 6 bytes, and they have given that frame size is nothing but 4 bytes. Okay, I am writing 4 as 2 power 2 bytes. So 2 power 6 divided by 2 square is 4, which is nothing but 2 power 4. It is nothing but 2 power 4 frames or 16 frames. Okay, see, it is nothing but 64 divided by 4. 64 divided by 4 is 16, right? Anyway, I just written in terms of 2 power. Okay, it will be helpful when we actually go for a bigger example. Here we are taking a small example. Anyway, let's see this. And what is the number of pages? Number of pages really depends on, see, what is maybe number of pages is, they have given that, let us assume this is the process, okay, this is the logical address space, and they have given that the size of process is 16 bytes, right? 16 bytes. Also, they have given that size of a single page is 4 bytes. Okay, single page is 4 bytes. Now, 4 bytes. Now, how many such pages will be present in this process? 16 divided by 4 is nothing but 4, right? So, we will have exactly 4 pages. Now, how did I get this 4? Number of pages is nothing but logical address space divided by page size. Logical address space is nothing but 16 bytes divided by 4 bytes. Okay, 16 divided by 4 bytes will get cancelled. 16 divided by 4 is nothing but 4. So, 4 pages. So, we have a total of 4 pages and we have a total of 16 frames. Okay, 16 frames are present inside the RAM. So, let me take the 16. Okay, so that will be easier to understand. It is 0th frame, first frame, second. This is 7th frame. This is 8th frame. This is 9th. This is 15. Okay, so there are 16 frames over here. So RAM has been divided into 16 frames. Okay, also our process has been divided into 4 pages. Now what I should be doing is I should be placing these 4 pages inside the RAM. Okay, depending on which frame is actually available. For example, let us assume this is occupied. Okay, this is occupied. 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 Okay, this is, as of now the RAM is looking like this, which means this frames has been occupied by some other process. Now I want to place this 4 pages inside the RAM. Okay, let us assume that, see, this is page number 0, okay, and this is page 1, page 2 and page 3. Similarly, this is frame 0, frame 1, frame 2 and so on. Okay, and this is frame number 15. Now let us assume page 0 is placed over here. Okay, page 0 is placed over here, page number 1 is placed over here, page number 2 is placed over here, and page number 3 is placed over here. Okay, so clearly here there is non-contiguous allocation, which means our process is placed in non-contiguous addresses of RAM. Fine, this works perfectly fine. Now my question is, how will the CPU actually execute process? Okay, let me name this process as P1. Okay, in case if it would have been contiguous allocation, what we could have done is, we could have just CPU should have loaded the base register of the process, and it could have executed line by line by using simple addition, right? We have already seen how it happens. Now let's see how here it happens. Okay, how CPU executes this process. What CPU will do is, CPU will maintain something called as page table for every process. Okay, for every process a page table will be maintained. For example, for this is very important. Okay, it is not that a page table is maintained for all the processes. That is wrong. A page table is maintained for every process. For example, here there is a process P1, right? For P1 there will be a page table which will be maintained. Now how the page table is nothing but a table. Okay, table is nothing but a collection of rows. Now what these rows will have is, see, the number of rows in this is a table. Okay, we say this as page table of P1. Now this table will have rows. The number of rows in this table depends on how many pages P1 has. See, this is a page table of P1, and the number of entries in page table of P1 really depends on how many pages P1 has. For example, P1 has 4 pages over here, right? And so this page table will have exactly 4 rows. This rows I can also say that as entries. Okay, 4 rows or 4 entries. Now what this entries will have is, this entry actually corresponds to page number 0. This corresponds to page number 1, page number 2, page number 3, which means this is entry number 0, entry number 1, entry number 2, entry number 3. Entry number 0 will actually indicate in which frame our page 0 of process is located. Okay, see, page 0 of P1 is located in frame number 3, right? Frame number 3, and so this entry will have frame number 3. Okay, frame number 3. Now this entry actually indicates where page number 1 is present, or frame number in which page number 1 of P1 is present. For example, page number 1 of P1 is present in frame number 5, and so this will contain frame number 5. Okay. Similarly, page 2 of P1 is actually present in frame number 7, and so this entry is nothing but frame number 7. Similarly, page 3 is present in frame number 9, and so this will contain frame number. Fine, this is how the page table is actually created, right? Now what will happen is, even this page table will also be placed in the frame of RAM. Okay, see, as of now our RAM has been divided into frames. Okay, so anything which we wanted to place inside the RAM should go in the form of pages. Okay, where page size equal to frame size, and so this page table has to be placed inside a single page. Now my question is, can this be placed inside a single page or not? See, what will be the size of this page table? First of all, what is the size of a single frame? It has been given that size of a single frame size is nothing but a frame size or page size. Okay, both are same, is nothing but 4 bytes. This is what is given in the question. Now what will be the size of this page table? There are exactly 4 entries. Fine, there are 4 entries. Now what will be the size of the entry? This is very important. What will be the size of a single entry? Okay, that really depends on frame number, right? See, how many bits do we need See, this is actually indicated in binary, okay? Frame number 3 will be indicated in binary. Now, how many bits do we need in a particular entry? What will be the size of a single entry really depends on how many frame numbers we want. For example, the number of frames we have in our RAM is nothing but 2 power 4, which means we need 16 frames, right? Now, in order to address 16 frames or in order to number 16 frames in binary, we need exactly 4 bits, right? We need 4 bits. So, this frame 3 will be indicated in binary as, for example, it will be indicated as 0011. Okay, similarly, this will be frame 5 will be indicated as 0101. See, it is very important why it is 4 bits. You need to understand it. Okay, it is 4 bits because we have a total of 16 frames. Now, in order to address 16 frames, we need 4 bits. That's why we've written the numbers in 4 bits. So, there are a total of 4 entries and every entry size will be exactly 4 bits. So, total size of our page table is nothing but 16 bits. Okay, it is not bytes, it is 16 bits. Now, in case if I wanted to convert it into bytes, what I should do? I should divide it by 8, right? In case if I divide it by 8, this will become in bytes. Okay, so 1 4 is 4, 2 4s are 8, 1 2 is 2, 2 2s are 4. So, totally there are 2 bytes. So, size of this page table is 2 bytes. Okay, so definitely we can place this complete page table inside the frame of RAM. Okay, we can place this complete page table inside the frame of RAM. Let us assume it is placed here. Page table of P1 is actually placed. See, everything will be present inside the RAM. Okay, so that's why I have placed the page table of P1 over here. One important point you need to notice here is, see, the size of the page table is 2 bytes. Okay, and also the frame size of the page table is 2 bytes and size of a frame is 4 bytes. So after placing this 2 bytes inside the frame, another 2 bytes will be actually left out. Okay, another 2 bytes will be free inside this frame. Now, can we use it for some other process? No, we cannot use it. So clearly there is internal fragmentation problem. Okay, so paging suffers from internal fragmentation problem. Okay, but one thing you need to understand is the internal fragmentation problem is very less. Okay, when can this happen? See, actually it didn't happen for our pages, right? Because page size equal to frame size. So it didn't happen for our pages, page 0, page 1, page 2. Here there is no internal fragmentation. Only for the page table which we maintain in order to keep track of the pages of our process, we came up with a slight internal fragmentation. Okay, so paging definitely suffers from internal fragmentation, but the amount of internal fragmentation is way too lesser than what we saw in fixed partitioning. Okay, in fixed partitioning, every process you place there will be internal fragmentation, but here it doesn't happen like that. Okay, only for page table it happens. For placing processes there will not be any internal fragmentation. And also now my question is, can we have internal fragmentation in case of processes? This is a very interesting question. Okay, can we have internal fragmentation? See, we have placed page 0 of P1, page 1 of P1, page 2 of P1, page 3 of P1. Can we have internal fragmentation over here? Yes, it is still possible, and it is possible only in this frame. Okay, internal fragmentation is possible only in this frame. Why? See, here actually process size is a multiple of frame size, right? For example, here they have given that frame size as 4 bytes and process size as 16 bytes. 16 bytes is a multiple of 4 bytes, right? 4 into 4 is 16. Now, in case if it would have been 15 bytes, what would have happened? In case if process size is 15 bytes, I could have placed 4 bytes over here, 4 bytes over here, 4 bytes over here, but I could have placed the remaining 3 bytes over here, right? So in 4 byte frame, I am just placing 3 bytes, whereas I am leaving out that one byte. Okay, so internal fragmentation is possible here only in the last page of a process and in the page table of the process. Okay, only in these two cases internal fragmentation can happen. It cannot happen in any other pages. So internal fragmentation in paging can happen in two places. Okay, can happen in 2 places. It is not will happen. Can happen either in the last page of the process and the page table of process. Okay, internal fragmentation is possible in paging. Fine. But external fragmentation cannot happen. Okay, external fragmentation will never happen. Why? Because we are actually following non-contiguous allocation, right? In non-contiguous allocation, definitely external fragmentation cannot happen. Fine. Now this page table has been placed over here, right? Now the most important point you need to understand here is, see, why are we really creating page table? We are creating page table because CPU wants to execute this process, okay? And it is not possible using simple addition like we did for contiguous allocation. Here, since paging is a non-contiguous allocation technique, we need to figure out some way through which our CPU will be able to take any line of our process, okay, which means any instruction of our process can be fetched by the CPU easily. So for that reason we have created this page table, and this page table has been placed over here. You can think of it like this table is exactly placed over here, okay, in this frame. Fine. Now let's see how CPU will execute this process.